Today, we want to turn our attention to the input of the primary variables of the current transformer model. In this diagram, we see three phasors. These are the load current, the short circuit current, and the voltage. Each phasor can be rotated. The numerical values on the right will change accordingly. Let us now clarify how the equivalent circuits look like for these phasors. Let's start with the load current. For the load current, we can draw the following equivalent circuit diagram. A generator with infinitely high short circuit power, a bus bar, a power line, another bus bar, and another generator here. And of course there must be a load which we place at the right bus bar. We measure the current at this point, that is the current flowing towards the load. Also we measure the voltage at the left bus bar. A power system can have different operating modes, and the load current can flow from the left generator as well as from the right one. If the reactive power is well compensated, then the load current is almost in phase with the voltage. If a lot of reactive power is drawn, then the current is lagging. If the current flows in the other direction, then it is here on the other side and is leading. Basically, there are no restrictions for the current phasor. It can take up any position in the diagram with respect to the voltage. Now we deal with the short circuit condition. In this case, the equivalent circuit looks a bit different because the second generator and the load have been disconnected by the short circuit. Again, the voltage is measured here, but it doesn't change as the left generator has a short circuit power that is infinitely high. However, we have a current flowing. This current is limited by an impedance comprising all resistances and all reactances lying in its path. The angle between the reactance and the resistance also corresponds to the phase shift between the voltage and the short circuit current. So if we draw the phasor diagram of the short circuit condition, we'll see that the short circuit current lags the voltage because a power line is an inductive element. The corresponding angle phi can be determined with the formula phi equals arcus tangens x divided by r. We can also write x divided by r as omega times L divided by r, or omega times Tp, where Tp is the grid time constant, also called primary time constant. It means that we can calculate the angle phi with the formula arcus tangens omega times Tp. The grid time constant is such a constant that determines the decay of the DC component of the short circuit current. This can be seen particularly well in the model. If the voltage and short circuit current phasors are placed together, the grid time constant is equal to 0. The more the two phasors diverge, the greater this time constant also becomes. One can increase it up to a value of 300 milliseconds. Here I would like to mention one more important point. It is about the dependence of the angle phi on the grid time constant Tp. Let me show this dependence graphically. On the x-axis we have Tp in milliseconds. On the y-axis we have the angle phi in degrees. The dependence of these two quantities is represented by the arcus tangens function. This function looks something like this. It has an asymptote at 90 degrees. If you enter a Tp value of 20 milliseconds as an example, it would correspond to an angle phi of slightly greater than 80 degrees. This means that the angle range from 0 to 80 degrees is covered by the Tp range from 0 to 20 milliseconds. All other time constants lie in the range of approximately 80 to 90 degrees. Therefore, A fine adjustment of Tp in this range is hardly possible. This can be seen in the phasor diagram. When we turn the phasor around 140 milliseconds, we see a sudden jump to 300 milliseconds. But you can also use the input field on the right and enter the value directly there. Alternatively, the size can be changed with the mouse wheel in the graph. The size can be finally adjusted by pressing the Shift key. Likewise, the mouse wheel can be used to change the phasor sizes so that both the small load current and the short circuit current are more visible. But how do we get from the phasor diagram to the sine wave forms? And how can we understand what phasor position results in the largest DC offset? For this purpose, we can imagine that the saturation curve isn't there, as well as all these values, and use this diagram for the graphical explanation. As we know from the theory on alternating current, there is a connection between the phasor and the sinusoidal quantities. If we have a rotating phasor of one magnitude, then its projection on the imaginary axis gives the instantaneous value of the sine wave of that magnitude. If we take, for example, the phase of the short circuit current, which rotates counterclockwise from this position, then its sinus curve will look something like this. The projection of the load current phasor will also result in a sine wave. In our representation, however, we draw it to the left of the amplitude axis, since it represents the state of the network before the fault occurred. What is important here is the fact that at the transition from normal operation to short circuit current at time 0, the instantaneous values of the load and short circuit currents are not the same. In the case of networks with inductive components, for instance a power line or a transformer, a sudden jump of the current is not possible. However, the jump doesn't occur because it gets compensated by the so-called DC offset. This magnitude here is the DC offset. It can be expressed by this E function, where A is this magnitude in the graph, the initial value of the DC offset. This means that the sine curve of the short circuit current is shifted upwards by this magnitude A and then continues its course. From the phasor diagram on the left, the magnitude of A can be easily determined. This is the projection of the geometric subtraction of the load current and the short circuit current on the imaginary axis. Therefore, it is clear that for the largest initial value of the DC offset, the fault inception angle of the voltage must be rotated in such a manner that the two projections, that is, these two lines, coincide. In the sinusoidal curves below, this maximum value can be seen on this narrow line. If you increase the fault inception angle so that this time the two upper lines coincide, then the initial value of the DC component becomes 0, which can be seen below. The narrow line disappears and the current curve is not shifted. If the fault inception angle is turned to the third quadrant, then a maximum displacement can also be set there. As we can see, the time Tz, that is the time at which the CT saturates, depends very much on the size of the DC offset. If we have approximately 30 milliseconds in this position, then the saturation here is not present at all. But we'll delve into this in more detail in the next video. An important point that needs to be addressed is that the voltage phasor is not subject to any change in scale because it is, so to speak, only an auxiliary phasor, which is only there to change the fault inception angle. I think that by now everything should be comprehensible with the input of primary quantities. In the following video, we'll take a closer look at the CT characteristics and the meaning of the other diagrams. Thank you very much for your attention. See you in the next video.